So no, nice. Okay, so we will continue. Where did we stop? Okay, yesterday the last thing that we discussed about was storing input in a Turing machine, right? But now we'll start getting into the main thing. So the first thing that is there is something called this is not in the notes. It's from the extra class that sir took from me, so I have to write as well. So there's something called, is the spelling right? Acceptance problem of DFA. And wait, what problem? So acceptance problem of DFA. And I told you, right, every problem is a language, every language is a problem. Let's see how does this look like. So ADFA is a representation. This represents the acceptance problem of DFA. What does it have? It has a tuple. It has a tuple d comma w, where d is a machine. We know what's a machine, right? And what kind of a machine? Here it's a DFA. So D is a DFA, and we know DFAs are five tuples. So D itself is a five tuple, but we are representing that five tuple using a letter called D, and here D is a DFA, and W is some string. So W comes from sigma star. So if sigma is the alphabet, sigma star is the collection of all strings, right? So W comes from sigma star. It's a string essentially. So let me just write. Uh, Fine. It means W comes from sigma star. And when does this d comma w, like, what kinds of d comma w will you find in ADFA? They have to satisfy some property. The property is this one: w is a string that is accepted by the DFAD. It is accepted by D. So in other words, I could also write it this way, right? W belongs to the language of D, because language of D is basically the set of all strings accepted by D. So W must belong there. So if this is the condition that is satisfied, then I will just take the tuple and put it in ADFA. So ADFA is a collection of all these tuples. Now, how is this a problem? See, I can basically represent anything in terms of zeros and ones. So there is some string corresponding to this. Like previously, we converted an entire language into an infinitely long binary string, right? So there are ways to convert this tuple into a binary string. So that is uh, uh, and what does it do to ADFA? It makes ADFA a language, right? So that is why, uh, and we know that languages are problems and problems are languages. So this is a problem. So what I'm telling is, if ADFA is there, you will have some tuples, right? You will have D1 comma W1. Uh, I mean, you can have the same machine. There is, and then you can have D2 comma W2. All of this is fine. Uh, how can this be a language? If I convert each of these tuples into some binary strings, then my ADFA will then become a subset of sigma star, and anything that is a subset of sigma star is a language, right? And if it's a language, it's a problem. So that is how it goes. Fine. So this is we defined something called the acceptance problem of DFA. Now what we are supposed to do is uh, okay, let me see what you're supposed to do. Okay, fine. So the question here is there any machine that recognizes this ADFA? Is there any machine? Or it's like we know that the language of D will be always recognized by D, right? So is there any machine that recognizes this language? That is the question. Is that the question? Fine. Before we get into all of that, let's see. So let's say I have a tuple D comma W. Let's say I have a tuple D comma W. It's either going to be in ADFA or it's not going to be in ADFA. When is this going to uh, be in this ADFA? If W is accepted by D, then it is going to be in ADFA. This is going to be in ADFA. If it is not accepted by, if W is not accepted by D, then this tuple will not be in ADFA. That is fine. So just 1 minute. What did I write here? Okay, so here the question is, suppose I give you a tuple like this. Now you have to say whether it's in an ADFA or not. If I give you this tuple, you have to say if it's in an ADFA or not. So how do we do that? Is there any machine that's going to take this as an input and then tell us if this is in ADFA or not in ADFA? Simple thing is what you do. Let's say, okay, for now I'll just write input is you have some tuple, and we know that this is some DFA and this is some string. Now we have to make a machine. So since we are dealing with machines, okay, here this is the constructing Turing machines part. So I don't think they will ask you to construct a Turing machine, right? They told they won't ask you to construct a Turing machine. But fine, let me just go on because eh, I'll just tell you the thing. I see if it's not in the syllabus, it is well and good. But if it is in the syllabus and if I don't tell it, that will be a problem. So I'm just telling the things. So here, what we're doing is we're creating a Turing machine called M. This M is supposed to tell us if the given input belongs to ADFA or not. So we usually write it this way. So when I get the input D comma W, what am I supposed to do? In the input, what am I getting? I'm getting D as well as W. So I can use D and W in whatever way I want to. So what I'll do is I will run D on W. So what do I mean run D on W? It means I'm giving W as input to D. What will D do? Since D is a DFA, after reading the entire input, DFA will either reject this string or accept this string. So I have two cases now. If D accepts W, then what does it mean? Then it means D comma W belongs to ADFA, right? So that would mean now my machine M, my Turing machine M, accepts the tuple D comma W. or else what is it supposed to do? Or else M is supposed to reject the tuple. So this is one Turing machine that uh, that solves the problem. It's given an input d comma w, it's going to tell whether the input is going to be in a DFA or not in a DFA. So let me just like M tells if t comma w is in ADFA or not. So since this is a Turing machine, we know that there is something called a recognizer and there's something called a decider. Recognizer is our plain old Turing machine, but decider is something that halts at every input. So is this Turing machine a decider or a recognizer? It is a decider because to this Turing machine I will keep giving let's say d1 comma w. Oh, let me write it fresh. My input will look like this: d1 comma w, d2 comma w2, and so on. I keep giving input. The moment it reads this input, it's going to perform this algorithm. So what is going to happen? You will get the answer whether this is accepted or this is rejected. See, what does it mean when a Turing machine is either accepting or rejecting? It means you're either moving into the Q accept state or the Q reject state. And what happens when you go into Q accept state or Q reject state? The machine halts. So if you look at this, the Turing machine is halting at every input. And what is a Turing machine that halts at every input? It's a decider. So that would mean this halts at every input, right? M halts at every input. Halts, is that a T? M halts at every input. This makes M a decider. So M is a decider. Okay, fine. That was the acceptance problem of DFA. Now, similarly, let me just put a star. Acceptance problem of DFA. There is something else called the. I don't have to write the heading now. There's something called the acceptance problem of a Turing machine, and it looks like this. It's the same thing. Now you have a machine and a string as an input. It's the same story. Now this is only true if wait, let me write it here. Is accepted by DFA D. So here W is accepted by Turing machine M. So this is the acceptance problem of Turing machines. Now the questions here are, there are some questions. Is ATM Turing recognizable? So okay, what about this one? Is ADFA Turing? What is this? Is see, for solving the problem of ADFA, we have what do we have a machine M, right? So that would mean ADFA is Turing decidable, isn't it? Right? Because if I collect all the tuples that M accepts in this case, that would form my ADFA, which would mean my let me shift this down. So the language of M in this case is ADFA, isn't it? So my language of M, let me divide this into points. So here we have this, here we have this, here we have this, here we have this, here we have this. And one more thing is language of M in this case is ADFA. And we know that M is a decider. That would make ADFA Turing decidable. Nice. So ADFA is Turing decidable. Now we have something called ATM, the acceptance problem of Turing machine. Now one question is ATM Turing recognizable? The other question is ATM Turing decidable? Turing decidable. We'll first solve the first question. The answer is yes. Why? If the answer is yes, it means now I'm supposed to show that there exists a Turing machine that accepts these kinds of. Uh, I'm calling it tuples. You could think of them as strings because I don't know. I can convert everything to basically zeros and ones. So this is essentially some other string. Or I'll just call it m comma w. That's fine. So m comma w. So I have to construct a machine that uh, accepts m comma w, right? So we'll see. So I'm creating something called a universal Turing machine, and it looks like this. Uh, this answer is yes, and we'll see why. So I'm constructing something called a universal Turing machine, which is U. Fine. Mm, and how does it work? So if you have an input which looks like m comma w, what are we supposed to do? We know that m is a Turing machine and w is a string. So I can give uh, run m on w. So I can give my string as an input to m. So what is going to happen? If I give an input to the Turing machine, if it reaches the accept state, so if m accepts if m accepts w, then what am I supposed to say? If m accepts w, then it's nice, no? So it means this condition is satisfied. So I can say that uh, m comma w is a part of ATM. So in other words, it's simply you accepts. If m accepts w, then you must accept m comma w. So what does this mean? It means this universal Turing machine U. What does it do? It accepts m comma w's such where w is accepted by m. So it means my language of U is nothing but ATM. I did not say that U is a decider, and I didn't say that U is a decider. So as of now, we will see, not we will see, our plain old Turing machines are just recognizers, no? So this would make ATM Turing recognizable. If we show that U is decidable, then we can also say that ATM is Turing decidable. It's like Turing recognizable is a larger set. Turing decidable is a much smaller set. It's like more special. So in general, we can say ATM is Turing recognizable because it is because there exists a Turing machine that accepts strings of not strings or m comma w's like this, some tuples of this form. Now you might be thinking, see, if I give an input to a Turing machine, if it enters q accept, fine, you can say m accepts w. If it enters reject state, then fine, the machine will halt. What if it doesn't accept? What if it neither accepts nor rejects? Because we've seen that condition in Turing machines that can happen. It can keep going in loops. So that is like that's a problem. You wouldn't know, right? So even if you give here, we are not bothered about the time. If you give infinite time and it's like it's neither accepting nor rejecting, then we won't consider that, right? We don't have an else case here. We are not bothered. Only if it accepts, then we will take it. If it doesn't accept, then we are least bothered. We don't know if it's rejected or if it's something else, but we are least bothered. Here also we are least bothered, right? We're only looking at strings that are accepted by M. We're not looking at the other cases. The other cases where W is either rejected or W is in between. It's neither accepted nor rejected. It's the machine is still computing. It's going in loops. But we're least bothered about them. We got what we require. We only have to see if W is accepted by M. If W is accepted by M, then the this tuple M comma W is going to be accepted by our machine. In this case, our machine is U, and U is a recognizer, and its language is Turing recognizable. Uh, okay, that was the first question. The second question is ATM Turing decidable? So now the main question is ATM Turing recognizable? The answer is no. So we'll see why. So proof by contradiction now. We'll use proof by contradiction. So let's say, so let's suppose ATM is Turing decidable. So let's suppose the acceptance problem of Turing machine is Turing decidable. So what does that mean? If something is Turing decidable, then I can say that there exists a decider. I'm calling it U now. So there exists a decider U for my problem, right? ATM. So there exists a decider U where U is a Turing machine. That is understandable. Decider means a Turing machine that halts at every input. So yes, so that is what it means, right? So on every input, which looks like this, on every input that looks like M comma W, U is going to halt. So U halts. In the previous case, is there something called halting? No, because when I run W on M, U there is a case where you neither going to Q accept nor Q reject. So in that case, it's not halting, right? But we are not bothered about it because it's just a recognizer. If it finds accept state, it's fine. If it doesn't find an accept state, then we are least bothered about it. But decider is that's not the case for a decider. A decider means if you give any input, then it has to halt, or else that can't be a decider, right? So we'll see if such a decider exists or not. We know the answer. I mean, I told no. We'll see why it's no. Proof by contradiction. We're doing no. So what does this mean? It's like for a machine, if you give any input that's that looks like this. So if you give any input, so this is the input. If you give any input to the machine U, it's either going to give you accept or reject. So no in between, accept or reject. That is that that that, that is the characteristic property of a decider, right? So accept or reject. It halts. U halts. What does it mean when it halts? It's either accept or reject. So if you give an input, U is going to directly tell you accept or reject. So we'll see if such a U exists or not. So what I'll do now is uh, I will just write something now. So M1, M2, M4, and so on. Now W is a string, right? And I told you that I can convert literally anything into a string. So in this case, what I'll try to do now is I will convert this machine to a string. So machine is a five tuple. So it has some information, right? It has no, not a five tuple. This M is a Turing machine, right? So machine is a seven tuple. It has some information. I can convert literally any information to binary string. So that would mean there exists some binary string that represents this M. So I would call that this one the description of M. So if M is a machine, let me write here. So M is a machine, right? M is a Turing machine, and M is a seven tuple, right? So I'm using some new notation. So this is nothing but this is the description of M. So what kind of a description? It has like all the necessary information about M. It is in the string. So since it's a string, my or what is it going to? It's a string. So this is a string. I have nothing more to say. This description is a string. So the idea is I my W can be these strings as well, right? I mean, W is a string, so there is no harm in using the description of the machine itself as a string. So I will try to write that here. So the idea behind writing this is it's like I will give M1 comma description M1, M2 comma description M1, M3 comma description M1 as input. So we'll see what's going to happen. If I can convert every machine to a string, I think I can convert every string to a machine. So it means for any string is going to lie in this. Any string is going to be the description of some machine, and it's going to lie here. Similarly, uh, any string can be a machine. Is that far fetched? Maybe. So it's fine. The Okay, I'll go the other way around. I can convert any machine to a string, so that is fine. That is fine. So okay, fine. I'll take back my words. Maybe not every string can represent a Turing machine. Uh, but the other way, I can convert every machine to a string. That is possible because machine is a seven tuple. It has some information. I can convert it to binary in zeros and ones. That would make it a binary string. So fine. The contradiction arises here itself. So because contradiction means it's like, see, if you say ATM is Turing decidable, then it should be true for all cases. Even if something is going wrong, that means it's contradiction. So I will currently not worry about strings that don't represent a machine. I will only worry about the strings that are basically descriptions of the machines at this point of time. So what is U going to do? See, since by assumption U is a decider, so if it gets M1 comma description of M1 as input, what is it going to do? It's either going to accept or reject. Same is the story for every other input. It's either going to accept or reject. So this is how my U is going to function. It's either going to accept or reject, accept or reject, accept or reject. Nice. So this is how U is going to function. It's either going to accept, reject, and so on. This is U. This is how U is functioning. U. U when M comma description of M is given as an input. I am not giving it every possible string. The string is given in such a way that it represents. It need not be the same thing. So let me say Mi comma Mj. So I'm giving a machine comma description of some other Turing machine as input. It can be the same as well. There is no restriction. So this is the table, right? This is the table. Uh, Fine. So fine, this is fine. So now what I'll do is I will create one more machine is that is D. So D is another Turing machine. This is another Turing machine. So what does D do? D is the complete opposite of U, in the sense if U accepts, then D rejects, and vice versa is also true. If U rejects, then D accepts. So D is the complete opposite of U. So how is its table going to look like? Everything is same. The only thing that's D and U are the same things, but then the okay, I didn't write opposite, complete opposite. Everything is same, but the only thing that's different is the response. So it's the same thing. I'll just copy this. The only thing that's changing is instead of accept reject, it's either reject accept. It's like the opposite. So if you accepts, D rejects. If U rejects, then D accepts. So this is also a decider, right? For every input, you're either accepting or rejecting. So U is a decider and D is also a decider. This is another decider. Nice. U is a decider, D is another decider. Its decisions are opposite. Okay, fine. I'll not get into puns. Fine. So we have U, we have D. Now what is going to happen? Let's see. See, D is a decider. So D is a Turing machine itself, right? D is a Turing machine in itself. So if D is a Turing machine, that would mean D will appear. D is nothing but D is one of since M1, M2, M3, and all are Turing machines. So D will appear somewhere over here or over here. Like, I mean, not or, it will appear here as well as here. So D is going to appear somewhere. So what would that mean? It would mean so D is going to be somewhere here. And similarly, uh, its description is going to be somewhere over here. So what is its corresponding input? So at one point I will get D comma description of D as an input, and this is the U table, right? This is a table of U. Same thing is going to happen in D as well. This is D. In D, what is going to happen? Everything is opposite, no? So you get reject, accept, reject, accept. So where are we right now? We are just like we found D somewhere in one of M1, M2, M3, and so on. That would also mean the description of D is lying somewhere here. Because I told that on the top we have descriptions of Turing machines, right? And D is a Turing machine, so you'll also find the description of D somewhere along here. That is fine. So what is going to happen? So when you get this as input, since I know that U is a decider, this is either accept or this is reject. And D is defined in such a way that if U accepts, then this is going to reject. If U rejects, D is going to accept. So we'll look at both cases. Let's see if U accepts D comma description of D. What does it mean? When is U going to accept this one? U is going to where is my U? U is going to accept A tuple only when the string is accepted by the machine, right? So W must be accepted by M. If that happens, then only U accepts. So the opposite is also true. If U accepts, it means what does this mean? This means D accepts. Uh, D accepts the description of D. That is the meaning. But we also know if U accepts the tuple, then this is the meaning. That is fine. But then D rejects. If U accepts, then D rejects, right? What does it mean if D rejects this tuple? Is there any meaning? If U accepts, then we understood this is there. What does it mean if D rejects this string? Or do you see a contradiction? If U accepts D comma description of D, then we know its meaning. The meaning there is D accepts the description of D. Here I'm saying D rejects the description D comma description of D. What does this mean? When is D going to reject something? Let me think. I mean, the first idea that's coming to my mind is if D rejects D comma description of D, that would mean D is not accepting this one, and this is a contradiction, right? But I'm just trying to check this one. Is this implication valid? I'm just trying to think. I'm just checking. If D rejects D comma description of D, does it mean D rejects description of D? Let me just see. Because U and D are exactly the same. It's just that if U accepts, D rejects. Hmm, this one minute. We'll look at the other example, other case as well. We'll just see if it's going to click. If u rejects d comma description of d, then I know that it means d rejects description of d. That is fine. Then d accepts description of d comma d. Does this mean d accepts description of d? I'm just checking if this implication is correct or not. If we can say, if we know that this is true, then we can directly see there is a contradiction. I'm just trying to see if moving from here to here is correct or not. Let me just think for a while. If we know that is true, then it is very much obvious there is a contradiction. uh, I mean, since we have less time, you can think about this later. I will also think about this later. I will move ahead. Mm, but this is apparently true, but okay, let me just think for a while. I don't think I should leave you hanging like this. um, you can think about it later. I will just proceed. I mean, just try think about the contradiction. Okay, so the languages of DFAs are regular languages. Then the languages of PDAs are context-free languages. Then uh, we have Turing recognizable languages, but then in itself we have a special set of languages called Turing decidable languages. Uh, and then we have outside languages that are outside this, so non-Turing recognizable. They're all proper subsets, right? It's like uh, a proper subsets in the sense I will always find I can always find one CFL that is not a regular language. I can always find one Turing decidable language that's not a CFL. I can always find one Turing recognizable language that's not Turing decidable, and so on. So they're all proper subsets in that sense. So, and Turing machines are not the only machines, right? I mean, uh, we can have problems that can't be recognized by any Turing machines. We proved the fact that there are uncountably many problems, but only countably many Turing machines. That would mean that there will be some languages outside this entire thing, which is not which are not Turing recognizable, and there are uncountably many, right? Turing recognizable, it's only countable. It's a uh, countably infinite set, but then the set of all problems is uncountable, basically uncountable. So you'll have many languages outside this one. So here the question is there uh, okay, let me see what is the question here. Okay, is there any trivial Turing unrecognizable language? So trivial in the sense, see, we know there are uncountably many problems, but is there any trivial problem? Trivial in the sense, like you can directly give an example. Okay, there is one Turing unrecognizable problem. Can you like trivially say that? Okay, this is pakka Turing unrecognizable, because that is how proper subsets work, right? If you find one language that is outside Turing recognizable, then you can say, okay, this is for pakka. See, for example, we looked at this case, right? If you have to show that, okay, give me a trivial example uh, of a context-free language that is not a regular language. One example is this one. Why am I writing with this color? For example, uh, so A is a CFL, but A is a context-free language, but not a regular language. So this is an example. Uh, like now, I can say that A is here. So A is a context-free language, but it's not a regular language. So this is like an example. Might not be trivial, but then I gave an example. But we need a trivial example as to what could that one language be that is outside Turing recognizable. We will see. But before we go there, we have some theorem. Star is not important. Star is basically the points. So this part got ended. So that is fine. They do not mean important points. I'm just marking down the points. So I'm writing a theorem here. The theorem is okay. So if there's a language L that is decidable, so if a language L is decidable, if there is some language that is decidable, then okay, fine. So a language L is decidable if and only if or like a language L is decidable if and only if L is Turing recognizable and L complement is also Turing recognizable. In other words, if I write this in other words, when can I say a language is undecidable? I can say L is undecidable if and only if L is Turing unrecognizable. It's like, see, I have P by implication Q. I can say that now, no, not Q. I have P imply by implies Q and R. Now, what would this mean? I can say that not P would imply uh, not Q and R. That would mean not Q or not R. So let me just write it. So L is uh, Turing unrecognizable, or L complement is Turing unrecognizable. I just wrote the same theorem, but I took the negation. So this is one theorem. Proof, we don't have to go through it though. There is a proof. I will just write the proof in the notes later. I will prove it later. You can go through it. Okay, fine. So the question that I asked you before was: is there any like uh, a trivial Turing unrecognizable language? Okay, I can give this one also. Where is ATM? I know that ATM is Turing recognizable, but it is not Turing decidable, right? So that would make ATM go here. And what was ADM? Not ADM. ADFA. ADFA was Turing decidable, but we didn't check if it is context free or not. So ADFA will fall somewhere over here, but where exactly you have to see. Uh, okay, but ATM lies here. ATM is not Turing decidable, but it is Turing recognizable, so it falls over there. So, and we are searching for that one trivial example that is Turing unrecognizable. So we'll see. Uh, okay, the answer goes like this. We know that the acceptance problem of Turing machine is undecidable. We know this. So if I use this property here, this would mean uh, what does this mean? This means ATM is uh, either Turing unrecognizable or ATM is ATM complement is Turing unrecognizable. But but we know that but we know that ATM is Turing recognizable. We know that we've seen that ATM is Turing recognizable because uh, we found a Turing machine that accepts this the input from ATM, which was essentially the universal Turing machine, right? So what does this mean? It means this is a false statement, and if this is false, then to make this entire or true, This has to become true. So that would mean ATM complement is Turing unrecognizable. So here is your trivial example for a Turing unrecognizable language. Now I can say that if someone asks you, give me, I know that every one of us know that there are uncountably many problems. That would mean there are many problems outside uh, Turing recognizable set. So what is one trivial example? You can directly say the complement of ATM is a Turing unrecognizable language. See, complement and all. How can I take? It's like a set, right? ATM uh, is a set of tuples which look like m comma w's. So whichever m comma w's are not accepted by, not about not accepted. It's like uh, okay, fine. Not accepted means for a Turing machine, it doesn't mean rejected. So keep that in mind. In DFA, if your string is not accepted, it means it's rejected. But in a Turing machine, if a string is if W is not accepted by a Turing machine, it doesn't mean it is rejected, because it is either rejected or it keeps going on in loops. So that problem is still there. So if you accepts this tuple, then it's going to be in ATM. If the opposite, in the sense, if it doesn't accept means it's either rejecting this or it's simply going in loops. So any of the two cases. So in short, if the universal Turing machine doesn't accept this string, then it's going to go and land up in ATM complement. So the collection of all such m comma w's will be found in ATM complement. What kinds of tuples? The tuples which were not accepted by the universal Turing machine. And mind you, not accepting means for a Turing machine, it's either rejected or it's moving in loops. You can't directly say it's rejected. Proof for this is not necessary. Like, even I did not discuss the proof of pumping lemma, right? It's in the notes. I will provide the proof later when I find the time to write all of this in the notes. I mean, it's going to be the same thing, only some, I think. I will think about this before writing the notes. I will think about this and provide a satisfying explanation, hopefully. We'll see. It's the same thing. Notes also will have the same thing, so you could look at this document. Uh, okay, so the re-entry. Now, class of P and class of NP are going to do a re-entry there. So, class of P we know, right? Uh, so, class of P are like set of problems that are solvable in polynomial time by a deterministic Turing machine with singleton. See, multi-tape and single tape, same thing. But then when time comes into picture, then I think they are different. But this is by definition. This is the definition of class of P. If you're not satisfying these conditions, then it won't be in class of P. The problem won't be in class of P. So class of P is set of problems that are solvable in polynomial time by a deterministic Turing machine with singleton. So let's say I'm defining some new notation. So okay, what is a new notation? We know big O of n, right? Big O of n is like it's like not big O of n, big O of. Okay, let me just write the notation. I think. So I'm defining something called nk. I mean, notation here is not important. You have to get the idea. That's it. So I'm defining this to be set of all problems solvable in polynomial time. right? It could be n power 999, n power 10,000, but still polynomial time. So if this is the notation, then I can say that p is nothing but it's the union set of all it's the union set of all problems solvable in uh, constant time, linear time, quadratic time, cubic time, biquadratic, and so on. Uh, Pentic, and I think pentic is the next one, and then it goes on. It's like k goes from like zero to whatever. So whatever the problem is solvable in polynomial time, you just collect all of those and dump it in class of p. Nice. I mean, solvable in all. I think I should mention by deterministic Turing machine. So this would make it class of p. Nice. I mean, it's just notation. That there's nothing. It's the same thing. I just rewrote something in words. Uh, I rewrote something that is in words in like using mathematical notation, but that's fine. You should get the basic idea. That's it. So class of p. Nice. There is something called class of np as well. Class of np. So everything is the same. Class of p only. Everything is the same. But then it is solved. The problems are solved by non deterministic Turing machine. So the n in NP comes from non-deterministic. It is NP doesn't mean non-polynomial time complexity. It's still polynomial. Class of NP, basically the same thing, but then you have this one. In class of NP, the problem is solved by a non-deterministic Turing machine. Whether the classes themselves are like exactly the same or not, we will see. We'll see. Uh, see. Yes, we'll see. I'm talking in terms of the definition. The definition is almost same. The only difference is you have a non-deterministic Turing machine. We know that Turing machines and non-deterministic and non-deterministic versions of Turing machines are equivalent in the sense they solve the same set of problems. But then now the time is coming into picture, so you can't treat them as the same thing. So apart from this, class of NP has an equivalent definition. Uh, it says a class of NP is also the set of problems that have efficient verifiers. In the sense, efficient in the sense polynomial time. Now, what is a verifier? We'll see. Verifier means in the sense some process exists. What does that process do? Uh, say let's say some process uh, uh, some process that verifies the solution. So verifier is some kind of a process that you do to verify the solution. So what does efficient verifier mean? So efficient verifier means you're doing some process that verifies the solution in polynomial time. So what does it mean when I say set of problems that have efficient verifiers? It means set of problems uh, whose solutions can be verified in polynomial time complexity. So what do I mean by verify? It's like, suppose you're given a solution, you're supposed to tell whether the solution actually solves the problem or not. So that is verification. And if the verification is, like, if you're able to do the verification in polynomial time, then that means you have the solution, or the problem has an efficient verifier. If the solutions that you provide to a problem have efficient verifiers, then if they can be verified in polynomial time, it means the problem has efficient verifiers. And the set of all such problems make up the class of NP. Uh, we'll just take it as true for now. We will not see why is this true and all. I mean, okay, we'll just see. For a deterministic Turing machine, how is the computation going to look like? For a we've seen this yesterday as well. Deterministic Turing machine, it's going to look like you start with the first configuration, then you move on to the second configuration, and then so on. Finally, let's say you reach the kth configuration, such that you either reach the accept state or reject state. So the machine halts, right? Then there will be no more computation. You stop over here. So this is how the how the deterministic Turing machine transitions from uh, one configuration to the other. Let's say this is polynomial time. It took polynomial time for the machine to come from C1 to Ck. That would mean there is a solution, right? So this represents some solution. This is some solution that like you got this solution in polynomial time. So that means whatever is this problem, it would be kept in the class of P, right? So this will go to class of P. Uh, Class of P. So this goes to class of P because you're using a deterministic Turing machine, single tape, and then the solution that you got, you got it in polynomial time. So this, whatever is the problem, it's going to go to class of P. Nice. So, but how does a non-deterministic Turing machine transition from one configuration to the other? If it starts from, let's say, one configuration, it's going to split into multiple configurations simultaneously. So it's going to look something like this. It's like, I don't know, it's up to the machine at this point. It's going to like branch and branch and branch and branch. So that is how it's going to look like. So if there is any problem that is being solved using non-deterministic Turing machine in polynomial time, it means this will go to the class of NP because it's using a non-deterministic Turing machine. So let's suppose there is some branch, let's say some branch. So I'll call this the accepting branch. Accepting branch because I would like to think that by at the end of this branch, the machine enters Q accept, and it halts over there. So I'm just calling that the accepting branch. So let's say this non-deterministic, this tree over here represents some problem that you're trying to solve, and the possible solutions could be this branch, this branch, this branch, this branch, or this branch. Like, you don't know if they're correct or not. It's like, let's say five people are there. Five people try to solve it in five different ways, and let's say one of them is correct. So you have to verify it, right? So how do you verify it? Let's say someone proposes this as the solution. Can you verify it? You can verify it, but then if you're able to verify the solution in polynomial time, which means whatever is the height of that branch, it's supposed to be in polynomial time, right? So if that is the case, then you can say, like, okay, this answer is wrong, this answer is right. So if you're able to do that in polynomial time, it means you have an efficient verifier. You're doing some process to verify if the answer is right or wrong, uh, and you're doing it in polynomial time. So efficient verifier. So, like, this is the idea behind saying that. See, I told you that such problems are kept in class of NP, right? And here I am telling you that the class of NP can also be called as the set of all problems that have efficient verifiers. So, like, what is the intuition here? See, it means if I have an accepting branch that looks like this, and if that branch is like in if the height of that branch is like a polynomial time, like polynomial in the sense with respect to the input, it could be the height of the tree could be n power 10 or n power 100 or whatever. If it's polynomial time, uh, then it means I can verify the solution in polynomial time as well, right? Can't I? It's like, uh, see, if someone gives me these set of configurations, I will just take that set of configurations and ask my machine to go through it. And finally, if it's the accepting branch, I will finally reach the accept state. So in this way, I verified if my solution is correct or wrong. And if that time taken is of polynomial time complexity, that would mean I have verified my solution in polynomial time complexity. So essentially, class of NP, which is the set of problems solvable in polynomial time using non-deterministic Turing machine. This set is also the set of problems that have efficient verifiers, in the sense the solutions can be verified in polynomial time. So that is why you can also use this one to describe what a class of NP is. Uh, okay, fine. Is there anything else in this one? So class of P, class of NP. Fine. So the next question is, now that you talked about the class of P and NP, now the next question. See, I am putting NP outside because uh, it may be uh, solves. We're just thinking maybe it's like P is a very special thing, right? P is like instead of non-deterministic, you're using deterministic. So we're just thinking that it's going to be smaller than this. It can't be the case that P is going to be bigger than NP, right? Because uh, why is it the case? Because if P is going to be big, if the diagram looks something like this, it means you'll have to find a problem that is in P but not in NP, which is, it doesn't seem that intuitive to us, right? Because P is using a deterministic Turing machine and solving a problem in polynomial time. NP is using a non-deterministic Turing machine and solving a problem in polynomial time. So it would only make sense that NP is like on the outside and P is in the inside. But now the next question is there any problem that is outside P but still in NP? So if you're able to find this, it means P is not equal to NP and P is a subset of NP. If you can prove that no such element exists, in that case, so I'll write two cases. P is a proper subset of NP, and the other case is P is equal to NP. If that is the case, then uh, you will find some element that is outside P but still inside NP. That is the case. Or else, if P is equal to NP, it means no such thing is there and it's just the same thing. So P equal to NP. There is no difference. Now the thing about this is, currently no one knows. So if you're able to answer this question, apparently someone told me it's $1 million problem. You can win money and fame. Uh, so no one knows. Does this exist? Does such an element exist out of P? I mean, is there any problem that is like outside P but still inside NP? Or you get the point, right? Is this true or is this true? No one knows. So apparently it's $1 million problem. So let me just write it somewhere. I didn't verify the facts. It's just that someone told me it's $1 million problem. I think it's uh, I don't know. I think there are some 7 questions. One of them is solved. Six questions remain. Something like that. I don't know. Just go through it. So we don't know. So as of now, we don't know if P is equal to NP or not. So this is called the uh, P versus NP problem, or whatever, P versus NP, simply P versus NP. You can Google it, it's fine. So, okay, we'll move on. Okay, now we'll move on to something called reductions. See, reduction is essentially converting an unknown problem to a known problem and then solving it. That is essentially reduction. Uh, I mean, we did something like this in Opti, right? Like converting an unknown problem into a known problem. Okay, anyways. So, reduction. So, how does reduction look like? So, I'll just draw a format. It's like, let's say you have an algorithm A which you want to like use, and then you have algorithm B as well, and let's say you're able to and you know how to use algorithm B. So like, okay, I mean, let's say algorithm B has a very nice solution, it gives out an efficient solution, but you have algorithm A with you and you want to find its solution. What is the solution of this? But let's say you're able to reduce, so I'm using the word reduce. If you're able to reduce A to B, I told you that B has a solution already, right? So just find that solution, and then later you can convert the solution of B in the format of the solution of A. So that is essentially how reduction works. But if this reduction itself is taking more than polynomial time complexity, that is useless, because let's say A is able to solve a problem in exponential time, and B is able to solve the another problem, but in polynomial time. Uh, and let's say there exists a way in which you can convert your problem A to problem B in polynomial time. So it's polynomial, poly reduction or whatever. Then it is good for us. So if I say if A takes exponential time and if B takes polynomial time, and if there exists a way, if there exists a way to reduce A to B in polynomial time, then it's good for me. No, I'll convert my algorithm A to algorithm B in polynomial time, solve my new problem now. I will get an efficient solution from algorithm B, and then whatever solution I get from algorithm B, I'll just convert it into the format of the solution of algorithm A. That's good, right? So this will only take polynomial time. So essentially, I have solved a problem which would require exponential time in polynomial time. That's good for us. But the problem is, if the reduction is not polynomial, if the reduction is not polynomial, then it's useless. Your final solution is going to be in exponential time. So instead of reducing it, simply uh, go ahead with the algorithm that you have. That would be better instead of reducing it to something else where the reduction itself is taking exponential time. So from now on, wherever I write the word reduce, we will assume that the reduction is taking polynomial time. Okay, so the format looks something like this. Uh, okay, I mean, okay, fine. There is some. Should I use the? Okay, fine. I'll just use it. So there's something called. Okay, uh, A is an algorithm, right? So see. the one algorithm could run on many different kinds of input, right? They will all have the same format and things. It's just that it's the same algorithm, but then your inputs could be of different forms. So now what I'll consider is, I will consider one input. So it's like an instance of A. So I'm considering instance I of A. So let's say, like, is A a problem or algorithm at this point? Uh, I think it's algorithm. So I'm taking one instance. So for example, let's say your input is your input to an algorithm is, let's say, uh, a graph. Let's say you have to input a graph. There are many, exponentially many graphs that you could make, right? So there are many graphs that you could make. So I'm just picking one of them. So I'm calling it an instance, and its name is I. So there is one instance of A. So it's like I have some input, some graph. It's not abstract or something. It's like, uh, I'm taking an example. So if I say a graph, I'm giving it some some graph. So it's like an instance of it. Fine. So I have an instance of it. Uh, before I give it to B, like before I give it to B, uh, B must be in a condition to understand whatever is the input of A, right? It can't directly take. For example, if the input of A is graph and if the input of B is a number, B can't take graph as an input, right? You have to convert this graph into a number. So there comes reduction. So there will be some function f that's going to convert this graph to a number. So what will happen? It's like f of I now. So I is a graph at this point. F of I is a number now. So what does f do? F converts the input of A to input of B. So f is like, it's doing pre-processing at this point. So after you convert it into the form of the input of algorithm B, now you can give the input to algorithm B. Now algorithm B is going to process it. So after, okay, so this is nothing. This is pre-processing. So after algorithm B gets the input, what is it going to do? It's either going to give you a solution or it's not going to give you a solution. So two cases. Uh, it's either going to give you a solution or not going to give you a solution. So let's say S is the solution. So if there is no solution, if algorithm B is giving you no solution, it means there is no solution for if there's no solution for f of I, it means there is no solution for I as well. So I is an instance of it. So it's like if I is some graph, it means f of I is some. For example, B takes number as an input. So f of I is some number. B algorithm processes that number, and then it's like finally there is no solution. If there's no solution, it means for the graph also there is no solution. So there is no solution for I. That is fine. What if there is a solution? Let's say S is a solution. Now your S is the number, but then A doesn't understand numbers, right? A understands only graphs. So now you have to convert this the solution that you got from B into the format of A. So let's say there is some function G. So G of S. So S is a number. So G of S is now a graph. And if your input is a graph, let's say your output is another graph. So G of S will be that graph or whatever is the format. It could be something else. So if the output is expected in terms of let's say an array, so G of S will be that array. So G of S is basically the solution of the instance I. So it's like now this is the solution for your algorithm A. So this G of S is the solution for I. So this is the solution for I. Solution for I, which is G of S. So this part is called post processing. So this is essentially how reduction looks like, but we want efficiency, right? So this conversion has to be efficient, and this algorithm should be efficient. Efficient in the sense polynomial time complexity, right? Is there any other thing that should be efficient? Probably even this one. Like if everything is efficient, so the entire reduction process is efficient. So nice. Uh, and so there is some other notation as well. Not notation, terminology. Class of P is also called easy. So so if I say some problem is easy, it means that problem belongs to class of P. So mathematically, there's something called easy. So if I say a problem is easy, it means the problem belongs to class of P. It's not the same easy that we use every day. It's like if a problem is in class of P, it means it's an easy problem. So if there is an easy problem, does it mean there is a hard problem? Yes. So we will see. We'll see what is a hard problem mathematically. So let's suppose. What did I write here? Suppose. So hard means you could think of it like this. So if there is no easy solution, it's hard. If it's not easy, it's hard. So you could think of it that way. For now, we'll see. Okay, suppose A is a hard problem. We haven't seen what exactly is hard, but we will think of it this way for now, that no easy solution exists. Easy means that it belongs to class of P, right? So let's say A is a problem. It is a hard problem. So for now we think it has no easy solution. Uh, okay, so if A is fine, this is our supposition. If A is reduced to B, and mind you, when I say reduction, we are doing the reduction in polynomial time. If A is reduced to B, so I told you A is a hard problem, right? It is pakka sure that we know A is a hard problem. If A is reduced to B, then B is also hard. So B is hard. So why is this the case? Because we will see, if B is easy, if B is easy, it means uh, I can reduce A to B. No, if I can reduce A to B, and if I say B is easy, B is easy means I can solve it in polynomial time, right? Using a deterministic Turing machine. If B is easy, and if I say that there exists reduction that can be done in polynomial time, that would also make A easy. Then A will become easy. But we know that A is supposed to be hard from the supposition. But we know that A is hard. So, but we know A is hard. So that would mean B can't be easy. And if B can't be easy, what did we say? If there is no easy solution, it means it has to be hard. So it means if we know A is hard, it means uh, there is no way in which you can reduce that problem to an easy problem. So B can't be easy in that case. Because if B is easy, it means then A is no longer hard. It's going to be an easy problem because you're going to reduce A to B in polynomial time and then solve B in polynomial time. That would make it easy, right? So if you know that A is a hard problem, then it means you can't reduce it to any other problem which is an easy problem. Or in other words, if you can't reduce a problem to any other easy problem, that means the problem that you have at hand is a hard problem. So we'll see what does hard mean. Like, is there a formal word for hard? Like easy means we have a class of P, right? So what is hard? We'll see. Uh, okay, so we will see. Are there problems? Okay, the question that we are trying to answer now is Are there problems which are the hardest problems, or it could be one problems in NP? So we'll try to answer this question. Uh, we'll see. So I mean, previously, what did we see? We saw that if there's any hard problem, I can't reduce it to any other simpler problem. And if I am able to reduce it, it means the problem to which I'm reducing my problem is also a hard problem. So it's like there's no escape. It's the hard problem. You can't escape from it. Because the moment you find an easy problem to which you can reduce your hard problem, the problem no longer becomes hard. It's going to be easy. So, but we know that A is a hard problem. So if you're able to reduce A to B, it means B is also a hard problem. Fine. So the other question that we want to move ahead, right? So are there problems which are the hardest problems in NP? So we'll just look at two conditions. If that is satisfied, it means the problem is the hardest problem. We'll see why. Uh, a problem A is, soon we are going to replace the word hardest by some other formal word. That's why I'm putting it in quotes. Is hardest, or is one of the hardest. Okay, let me just write. Or fine, we'll forget English for a while. A problem A is hardest in NP if two conditions are satisfied. The first condition is in NP means, first of all, is essentially A has to be in NP, that is there. The other condition is every problem B in NP, essentially every other problem in NP is uh, reducible. I mean, we want polynomial time reduction only, so polyreducible to A. It's like if you have your NP class and then you have a lot of problems, and let's say A is somewhere here. So A is going to be hardest if I can take every problem in NP, and if I'm able to reduce every other problem in NP to A, that would make A the hardest problem. Because why is it the hardest problem? Because if I solve A now, it means I would have solved every other problem in NP. That is why A is called the hardest problem. So it's like the main problem. It's like if I solve this, every other problem will be solved because I can reduce every other problem to A in polynomial time. So the formal, okay, let me just keep this diagram. A is like is the main boss or the final boss, something like that. Not fine. Okay, so the formal term is formal term for hardest in this case is you just replace hardest with NP complete. So what you've just seen is I'll write it once again. So a problem A is NP complete if the problem first of all belongs to class of NP, and then every other problem in NP, if every other problem in NP is reducible. I'm writing poly as well so that you don't forget. It is reducible to A. So if I solve A, it means every other problem in NP is going to be uh, solved. So NP complete. Nice. So NP complete is like a different set. Within NP, you have is NP complete? Yes. So within NP, you have something called NP complete. So you have something called NP hard as well. So NP hard has only one condition. It's like it's uh, okay. I'll just write the condition. A problem A is NP hard if every problem in NP. So if I take every problem in NP and if I can reduce it, if every problem in NP is reducible, polyreducible. So I mean, I'm not going to write it again. It is understood. Polynomial is understood because if it's not polynomial, it's useless. We want polynomial time reduction. Okay, so a problem A is NP hard if every problem in NP is reducible to A. But if you notice the difference between NP complete and NP hard, in NP complete you have this condition. The problem must belong to NP. But in this case, my problem need not belong to NP. That is the case. So if I draw the Venn diagram, okay, so what does this mean? It means, okay, let me first draw the Venn diagram. Two cases. We don't know if P is equal to NP or not, right? So I'll just do these two cases. So if P is not equal to NP, P will be here, NP will be here, NP complete will be somewhere over here. But NP hard need not be inside NP, right? It can be outside as well. So NP hard is probably this big thing is NP hard, and NP complete is a part of NP hard. So this entire thing is NP hard. This is NP hard. NP complete is here, and then you have NP. Will there be an intersection between NP complete and P? Let me just check if the Venn diagram is correct. Yes, so apparently there turns out to be no intersection. Fine. This is when NP P is not equal to NP. But let's say if they're equal, so what would that mean? In that case, we know P is equal to NP. That would also make it equal to NP complete. So this would look like this, and then you will have NP hard as well. So this will be NP hard. I mean, answering this is $1 million question. So I won't be uh, covering the solution, else you all will take the $1 million, right? So I won't tell you the solution. So okay, okay, okay. Is that the only thing? So what does it mean? What does it mean if a problem is not in NP? See, I told you that class of NP can also be described as the set of all problems that have efficient verifiers. So here, if you look at NP hard, you have problems that are not in NP. That would mean the solutions need not have efficient verifiers. Need not. It's not that it will never have, because NP hard problem can also be in NP complete, and if it's in NP complete, it will be in NP, and if it's in NP, you will have to have efficient verifiers. But if you look at it, some problems exist outside NP as well, within NP hard. So it would mean that NP hard problems need not have efficient verifiers. Uh, okay. So an example for a reduction would look like this. DAG is a problem that's like that asks you to find the longest path in G in a DAGG. You can do this in linear time using dynamic programming, that is fine. Let's say there is another problem S, which asks you to find the longest increasing subsequence. So when we were trying to solve this problem S, we kind of used DAGs, right? So we were literally employing reduction over there. So uh, if you remember, I can convert the problem S into the problem DAG in polynomial time, and then solve this, and then get back my solution. So because when we are trying to solve this, we are trying to essentially solve this DAG problem only. If you want, you can look into it on your own. So this is poly reduction. So easy reduction, maybe you can say easy reduction, because you're doing it in easy reduction. So easy, efficient, I think they keep popping up because polynomial time. Uh, okay, and hard in the sense, I just maybe just replace hard with the formal terms. So the formal terms are NP complete, NP hard, NP hard, NP complete, P, NP. Easy is kind of formal, but okay. Easy means class of P. That's it. So P and easy are the same things. You have NP, NP complete, NP hard. Okay. Uh, okay. The last thing I will be telling in this lecture is about the halting problem. I will simply say what is the halting problem, and then I will probably give you a list of things that you could be looking at, because after halting problem, sir did not tell me anything. He just gave me a list of problems to look at. I will probably share the list in the group soon, because it's becoming 10. I will stop this one here. TOC ends here, right? So in 5 minutes, I will stop this live stream. There will be a break of, I don't know, 30, 40 minutes. We'll see. And then I will look into graph algorithms. Okay, halting problem. What is the halting problem? So halting problem is like this. So let's say your input is some m comma w, where m is a Turing machine and w is a string. Same old story. But then now what you're supposed to do is, the question that you're supposed to answer is, uh, does m halt on w? If yes, then you're supposed to accept it. If no, then you're supposed to reject this tuple m comma w. So the answer is like is there any machine that does this? Is there any machine that answers this question? Apparently, this problem is undecidable. Undecidable in the sense, there exists no decider. There exists no decider to uh, is it recognizable or not? I didn't. I mean, you can think about it, but apparently, the answer to this question, like, it can't be answered by a decider. The proof, it goes something like this. Apparently, I think you can reduce it, ATM in the sense, the acceptance of Turing machine problem. You can reduce it to the halting problem. Is it possible? Can I reduce ATM to halting problem? Uh, I will think about this if I find some notes on this. I mean, find notes in the sense, write some notes on this. I will think about this later. Uh, Fine, it's 10 now. I have to leave. So halting problem is essentially this: you have an input. Input is Turing machine, comma. some string. Now it's like the machine, whatever that you're going to make, like is there any machine that uh, answers this question? So it's like if M halts on W, halts means either accept or reject. If M halts on W, then you can that machine is supposed to accept this, or else it's supposed to reject this. That is the thing here. So it's like if yes, then accept M comma W, or else don't reject it. I mean, else you reject it. Reject. So is there such a machine that answers this problem? The answer turns out to be that it's undecidable. In the sense, there is no decider. Whether there's a recognizer or not, you can think about it. Uh, Apparently, the proof goes this way, but I will have to think about this. I will see. So for now, I'll just provide you some list of problems that were supposedly discussed on Thursday. I do not know what happened on Thursday. So I'll just write some problems. So you don't have to break your head. I mean, I will maybe day after tomorrow I'll sit and go through these problems and then make notes for this. So we'll see. So it's like some something they discussed about these problems, like on the top, not in detail. So I will go through this later. So I will get back to you. You don't have to strain yourself or something. I don't know. Maximum independence. So I don't know. There were some problems. Like halting problem is one problem. Like we were discussed. Apparently something was discussed about it, and then some small things were discussed about these as well. So maybe I will get back to you later when I upload the notes. So I don't think maybe if you read the notes you will get it, but I have nothing to talk about these things. I did not go through any of these, and about some approximate solutions. It's, I think approximate solution to vertex cover, something like that. I'll have to see. I didn't see anything. So halting problem also maybe I'll have to look into it. I didn't write the proof, so it's not getting into my head. I don't remember what exactly happened. But the problem is this one. So is there any machine that answers this question? Apparently the answer is undecidable. Recognizable or not, you can think about it. We will see. Uh, okay, I mean, end of TOC. I have nothing more to say. I will try to write the notes and then upload later. Okay, I will stop the live.